Welcome to Relearn, a channel trying to make complex technologies and subjects understandable for everyone. Today, we are breaking down artificial intelligence, what it is and how it actually works in terms anyone can grasp. Why artificial intelligence matters. First, let's understand why artificial intelligence has become so important. Artificial intelligence marks the fourth major technological transformation in human history, the Fourth Industrial Revolution. The first revolution brought steam power and mechanization. The second introduced electricity and mass production. The third gave us computers and the internet. The fourth, artificial intelligence. Unlike other technologies of the past, artificial intelligence is unique because these systems can learn and make decisions. Unprecedented investment. Hundreds of billions of US dollars have been invested by tech companies in AI development. Global impact. Advanced artificial intelligence models like those from OpenAI, Anthropic, Google, and China have significant economic implications and are shaping geopolitical technology races. Workforce transformation. Many knowledge worker jobs will be transformed or replaced by AI integration. The nature of work is changing rapidly. Remarkable capabilities. Modern AI systems like GPT-4 have demonstrated professional-level performance on standardized tests, including US medical licensing and bar exams. How artificial intelligence works. Let us understand by a cake baking analogy. Suppose you have an artificial intelligence-powered assistant for making a cake recipe. It will use following steps. Step 1. Random recipe, random weights and biases. At first, our AI assistant has no idea how to bake a cake, so it starts with completely random guesses. It starts with 500 grams of sugar, 3 eggs, 1 kilogram of flour, and 1 cup of salt. In artificial intelligence terms, these initial guesses are the random weights and biases the system starts with. Step 2, taste test, input data and feedback. The AI bakes the cake using its random recipe and serves it to taste testers. The feedback is predictably bad, too salty, too sweet, terrible texture. The AI measures exactly how far off its cake is from perfection. This is the error or loss function. Step 3, tweaking the recipe, adjusting weights and biases. The AI makes small adjustments based on the feedback. Reduce salt to 1/2 cup. Lower sugar to 200 gram. Use 500 gram of flour instead of 1 kilogram. Step 4, repeat, training. This process repeats thousands or millions of times. Bake. Get feedback. Adjust recipe. Bake again. With each attempt, the AI's recipe gets slightly better. This is what AI researchers call backpropagation and gradient descent methods for fine-tuning the system. Step 5, making perfect cakes, inference. Once trained, the AI can consistently bake excellent cakes using its perfected recipe, the optimized weights and biases it learned during training. Artificial intelligence under the hood. At its core, artificial intelligence is just a bunch of numbers stored in matrices, representing weights and biases. Let us understand how these numbers do the magic. It starts with forward pass of input data. Input data is multiplied by weights, and biases are added. Output equals, input times weights, plus bias. An activation function, like sigmoid or ReLU, rectified linear output, adds nonlinearity, allowing the AI to model complex patterns. The output is compared to the actual target value, and the error, loss, is calculated. Through backpropagation, this error is used to adjust the weights and biases via gradient descent, minimizing the error over time. This process may repeat for millions of iterations until the model performs well. Core idea. The intelligence emerges from iteratively tuning these numerical values, weights and biases, to map inputs to desired outputs accurately. After simple analogy, let's take a more practical example and understand it more deeply. Imagine an AI that predicts pass, 1, or fail, 0, based on one input, Example exam score. Weights and biases, saved in memory, initially random numbers. Weight equals 0.8 single weight, matrix shape, 1 by 1. Bias equals -4.0 single bias. Input, for example, exam score equals 6/10. Input equals 0.6 normalized to range 0, 1. 2. How the AI uses these numbers. Multiply input by weight. 0.6, input, multiplied by 0.8, weight, equals 0.48. Add bias. 0.48 plus, -4.0, equals -3.52. Apply activation, sigmoid. Output equals 1 over, 1 plus e to the power, -3.52. Which is approximately 0.029, 3% pass chance. The AI predicts fail because 0.029 is less than 0.5. Training adjusts these numbers. If the correct answer was pass, the AI would tweak the weight and bias upward. Example weight equals 0.9, bias equals -3.5, to reduce error. After thousands of adjustments, it might settle on weight equals 2.5, bias equals -1.0. Now predicts pass for input greater than 0.4. If you want to know how backpropagation works, see the following calculations. You can also skip this part because you may not need to know the internal working of AI models to use them. In the pass-fail example explained just now, remember we had following initial weights and biases. Weight, 0.8. Bias, -4.0. Input, 0.6, normalized exam score of 6/10. Forward pass. Input multiplied by weight plus bias equals 0.6 times 0.8, plus, -4.0, equals -3.52. Apply sigmoid activation, 1 over, 1 plus e to the power, 3.52, 0.029. Predicted output, 0.029, which means fail since it is less than 0.5. First step. Calculate mean square error. Mean square error equals square of, actual minus predicted, equals square of, 1 minus 0.029, equals 0.942. Now things starts getting slightly complicated. Second step. 1. Calculate output gradient. Derivative of error with respect to output equals -2, actual, predicted, equals -2, 1 to 0.029, equals -1.942, here chain rule of finding derivatives is used. 2. Calculate derivative of the sigmoid function at our output. Sigmoid derivative, x, equals sigmoid, x, times, 1, sigmoid, x. Sigmoid derivative, -3.52, equals 0.029 times, 1 to 0.029, equals 0.028. Combining these, using the chain rule. Output gradient equals -1.942 times 0.028 equals -0.054. Third step. Calculate weight gradient. The weight gradient is derivative of error with respect to weight equals output gradient times input, which equals -0.054 times 0.6 equals -0.032. The bias gradient is simply the output gradient. Derivative of error with respect to bias equals -0.054. Step 4, update weights and bias. Assuming a learning rate of 0.1. Weight update equals learning rate times weight gradient. Weight update equals 0.1 times, -0.032, equals -0.0032. New weight equals 0.8 plus 0.0032 equals 0.8032. Bias update equals learning rate times bias gradient. Bias update equals 0.1 times, -0.054, equals -0.0054. New bias equals -4.0 plus 0.0054 equals -3.996. What's happening here? The network predicted 0.029, fail, when it should have predicted 1, pass. Backpropagation determined the weight needed to increase and the bias needed to become less negative. However, because we used a small learning rate, 0.1, the changes in a single step are tiny. Over thousands of iterations with many examples, these small adjustments would accumulate. And we may get final weight and bias as weight equals 2.5. Bias equals -1.0. How large language model works. The basic principle of large language model is same as in the pass-fail example just explained. But they are very complex, having billions of weights and biases set in various layers like input layer, hidden layers and output layer. Following things happen when you send a prompt to AI model. For example, prompt: what is pH of water? 1. Tokenization. The model first splits this prompt into tokens. It can understand what is pH of water. These tokens are assigned numerical ID. 2. Embeddings. These tokens are converted to high-dimensional vectors, embeddings. For example, pH may be converted to 7684096. 3. Processing through network layers. These embedding are passed through various layers having weights and biases. 4. Prediction. The model predict a token based on the embeddings. 5. Response generation. The model recognizes it is a question about pH of water through self-attention mechanism. The model generates one token at a time. For example, token that is generated first, then it is combined with prompt, and again a new prompt is passed again through network layers and a new token is generated. So at a time one token is generated and these tokens are again converted to a cohesive looking text. Like pure water at 25 degrees Celsius has a pH of 7, representing neutrality on the pH scale. Behind the scenes. Think of it like a super advanced text prediction system that has read millions of science textbooks, articles, and websites. Remembers patterns about how information is typically explained. Uses these patterns to create new, relevant responses to questions. Never actually understands chemistry, but has memorized how people talk about chemistry. The model doesn't look up the answer in a database, instead, it predicts what words would most likely appear. Based on all the text it has processed during training. Conclusion. At its core, artificial intelligence is a system of numbers, weights and biases, that have been optimized through repeated exposure to examples. The intelligence emerges from millions or billions of simple calculations working together, much like how billions of neurons in our brains collectively give rise to human intelligence. By understanding these fundamentals, you're better equipped to appreciate both the remarkable capabilities and the inherent limitations of modern AI systems, whether you're building them or simply using them in your daily life. Thanks for watching. If you like the video, please subscribe to channel and give feedback through comments.